All right, welcome back to Linear Algebra. We're going to get our work started in chapter 6, the last chapter of our course, talking about something called inner product spaces. Section 6.1 introduces them. And inner product spaces, roughly speaking, is the place where some geometry will come back into our vector space theory. We've been talking about linear algebra for the first part of the semester, and it's all been very algebraic. But there's a lot of geometry that you can do in a vector space when you have this notion of an inner product. It gives you a way to measure length and angles between vectors. So let's get started. I'm going to try to just sort of motivate the axioms that we'll look at below here by reminding you of something that you know from Calc 3 or Advanced Calc. In Calc 3, you usually talk about dot products on R3. I've written it here for Rn. But if you take a couple of vectors in Rn, what do we mean by the dot product of them? Well, you mean the sum of the products of the components of the vectors A and B. So you take A1 times B1, A2 times B2, and so on. You add them all up. That's called the dot product. Okay, you're familiar with some properties of it. It's a symmetric product. A dot B is B dot A. The dot product of a vector with itself is the square of the length of that vector. It's never negative. The only way it's zero is if the vector is zero. I'm not proving any of these things. These are just things that I'm kind of recalling from your calculus courses. Dot product distributes over addition. The dot product of A with B plus C is A dot B plus A dot C. And then the geometry, if you're giving me two vectors, neither one of which is zero, like in my little picture over here, they have an angle between them, an angle some measure between 0 and pi. The cosine of that angle is the dot product of A and B times the product of their lengths. If you solve that equation for A dot B, this is usually what I call the physicist's definition of dot product. A physicist will tell you the dot product of two vectors is the product of their lengths times the cosine of the angle between them. Okay, so that's all from calculus. So this is going to kind of motivate. We're going to abstract, extracting some of these properties, not all, but a minimal set of them that we can deduce the rest of them from. So let's make that main definition right now. Everywhere in this section, and this has kind of been true for our whole course because not all of us have experience with abstract fields, but in particular in this section, it's required that the field either be the field of real numbers or complex numbers. Because as you'll see in our definition, I'm going to be talking about complex conjugates, and that only makes sense for the field of complex numbers or real numbers, but the complex conjugate of a real number is just itself. Right. In fact, that characterizes real numbers. Real numbers are complex numbers that are their own conjugates. Okay, so this is the definition. When what I mean by an inner product on a vector space over the complex or real field, it's a two-variable function from the vector space into the scalar field. Instead of giving that function a function name like little f or little g or something, I'm just going to write the output of it. So a pair of vectors x, y, and v cross v is sent to something that I'm going to write x comma y with brackets around it. And I pronounce that the inner product of x and y. The inner product of x with y is how you pronounce that thing out loud. And it's a scalar. It's an element of the scalar field. And then the axioms, the things I'm going to assume is for every three vectors and every scalar, well, that first of all, that inner product is additive in the first coordinate. So if you take the inner product of x plus y with z, you get the inner product of x plus z and the inner products of y plus z. It also is scales in the first coordinate. So if A is a scalar, the inner product of AX with Y is A times the inner product of X with Y, and that makes sense. Remember, the inner product is a scalar, A is a scalar, so this is just the multiplication in R or C. So those two facts together mean that it's linear in the first coordinate. The inner product is linear. It's not always commutative. The inner product of X and Y with X are not the same, but they are complex conjugates of each other. So the inner product of x with y, if you switch the order, you put y before x, you have to take the complex conjugate. If it's a real inner product, then it's symmetric. Okay, or it's commutative. Xy is yx. But if it's not real, then you have to put that complex conjugate. These are all axioms. And then for any non-zero vector, the inner product of a vector with itself, first of all, it's implicit in my notation here that it's real because I'm talking about it being greater than zero. Complex numbers don't have an order on them. So the inner product of a non-zero vector with itself is a real number that's never negative. Okay, so that's what I mean by an inner product. I'm going to kind of go through a laundry list of examples. In each example, what I should do is verify these four axioms. In each example, I'm going to specify a vector space V. I'm going to specify this function, this inner product, and then really I should verify the four axioms. I'm not going to put the verifications in this video. We'll do a couple of them in class, but to keep the video kind of short, I'm just going to list these things. You can check out your book. So the first one, V is complex n space. Vectors in it are n tuples of complex numbers. I'll write their coordinates, xi's. If a vector is called y, then I'll write its coordinate yi. And by definition, the inner product of x with y is the sum of the product of xi with yi bar. Okay, so coordinate by coordinate, you take x1, y1 bar, add to it x2 times y2 bar, and so on, all the way to the last coordinate, xn times yn bar. Okay, that's an inner product on Cn, I claim. We'll check it out in class. If V is Rn, it's the same definition really, but if Y is a real number, then Yi bar is Yi. So when I reduce that thing, if the field is the real numbers, if these vectors are the real numbers, then that inner product is just Xi times Yi bar. That's the dot product. This is just the dot product from calculus. So the dot product is an example of an inner product. We're going to call both examples 1 and 2 so-called standard inner product. So the standard inner product is these things. On Cn, it's xi times yi bar summed. Yeah, on Rn, it's just xi times yi bar summed. Good. Yi summed, no bar. You can put the bar here, it doesn't hurt. But if y is a real number, yi is yi bar. Third example is kind of an exciting one we'll use a lot. It's an infinite dimensional vector space, continuous functions, say on a compact interval, closed interval. The inner product of two functions is just defined to be the integral of their product over the interval. All right, so without checking the axioms, I can at least say given f and g, this certainly produces a real number. The definite integral of f times g is going to exist because f and g are both continuous, and that integral is going to be a real number. And that definition satisfies those four axioms. Maybe that's the one we'll verify in class. All right, fourth and final example for this conversation, if you take the square matrices over the complex numbers, maybe before I talk about the inner product, if you give me a complex matrix B by its adjoint, I mean the transpose of its conjugate. How do I conjugate a matrix? I conjugate every entry. So B bar is the matrix whose entries are just the complex conjugate entries of B. All right, so I define an inner product on the square matrices by saying that A inner product with B is the trace of B star times A. So there's a little bit of a mystery of why to turn it around there. Maybe this is an example we could try to verify in class. All right, so all four of these things satisfy those four axioms. They're inner products on a vector space. When you put an inner product on a vector space for terminology, we're just going to call it an inner product space. So an inner product space, again, always over R or C for our purposes. It's a vector space over that field together with an inner product. So say, for example, in our first example above, Cn is an inner product space because it's the vector space Cn with the standard inner product. Same for Rn. This one that's still visible, square matrices is an inner product space because it's a vector space with this inner product. A given vector space might have many inner products on it. There's not just one. So that's why we have to kind of say that, well, it's the vector space together with this function satisfies these axioms. Let's look at some properties. I'm not going to prove all of these here. Maybe we can prove some in class. Some are going to be exercises, but they're just kind of properties that you can deduce from the axioms. So what do they say? One of the axioms says that inner products are linear additive, in the first coordinate. Well, they're additive in the second coordinate as well. I've actually got a proof of that down here. Let's check it out. If you give me three vectors and you look at the inner product of, say, x with y plus z, well, I can switch the order if I conjugate. Yeah, it's additive in the first coordinate. So the inner product of y plus z with x splits up under that conjugate bar, but the conjugate bar is additive, right? The conjugate of the sum of two complex numbers is the sum of the conjugates, and you just flip them back. So that's how you prove part A. Cool. Part B says that it's not doesn't scale in the second coordinate, but the scalar comes out with a complex conjugate. So those two properties mean that it's not quite linear in the second coordinate. People call it kind of conjugate linear. So what do I mean by conjugate linear? Well, I mean that it's additive, and when the scalar comes out, it comes out with a complex conjugate on it. Okay. Third property I'm not going to include the proof of here is that the inner product of anything with the zero vector is always zero. We said that the inner product of a non-zero vector with itself is always positive. If you get the inner product of a vector and it, with itself is zero, the only way that can happen is if the vector is zero. Okay, it's a property. I'm not proving it here. I am going to look at a proof of this one, that if you take the inner product of, say, x and y and x and z, and it's always the same for every x, then y has to be z. This thing we'll use actually as kind of a device. One way, sometimes we'll be wanting to prove two vectors in an inner product space are equal. And the way we'll do it is we'll show that their inner product with an arbitrary vector is always the same. Seems a little bit of a weird way to show equality, but it turns out to be handy. To try to prove E, I'm gonna be able to do it if you'll allow me to use the borrowed fact D for a second. So I'm going to use D in my proof down here. Maybe I can try to leave those visible. So how would I prove E? Well, suppose I have a couple of vectors that the inner product of them with X is the same for every X. Well, subtract, so the inner product's difference would be zero, right? But we just proved it's additive in the second coordinate. So that's going to be equal to zero for all X. So I can strategically pick the X, pick X to be Y minus Z. And the inner product of Y minus Z with itself is zero. So by part D, Y minus Z has to be zero. Cool. Stop the video and kind of let that soak in. Make sure you understand it. I'm going to just keep plowing along here. Inner products give us a way of talking about length in any vector space. Here's how. So given an inner product space V, so it's a vector space together with an inner product. If you pick an X in V, I'm going to define, we're going to call it the norm. You can also call it the length, but I'll use the word norm most of the time. The length of a vector X, the norm of X, is the square root of the inner product of X with itself. All right. That makes sense. We've said in any inner product space that the inner product of a vector X with itself axiomatically is always positive. If X isn't zero, if X is zero, you'll get zero. So we're not writing a number under there that we can't take the square root of. So if this is an inner product space over R or C, please notice that this norm is actually always a real number. It's the square root of a positive real number or a non-negative real number, so it's real. So the norm of a vector. You're used to this. If you take, say, the standard inner product space R2, so if a vector x has coordinates x1 and x2, the inner product of x with itself would just be the sum of the squares of the coordinates. So you take the square root of that, yeah, you get length. Yeah, the same thing is for vectors with n components. If you take it over the complex numbers, well, when you take the inner product of x with itself, it's xi times xi bar. Maybe you remember that multiplying a complex number by its conjugate gives you the square of its length in the complex plane, the modulus of that complex number. So you can kind of rewrite that formula. The length of x, the norm of x, is just the sum of the square root of the sum of the squares of the components. Right, so it's just the distance, the usual distance formula. If your vector only has one component, this norm is nothing more than its absolute value. It's length. Let's look at another theorem here. I've got proof of part A written here. So you take an inner product space, take a couple of vectors in it and a scalar. Well, first of all, the scalar comes out of the norm. These are properties of the norm. But it comes out with its absolute value bars. So we can take a look at the proof of that here. If you take a look at the norm of Cx, well, by the definition, it's the square root of the sum of C times xi squared. but by properties of the absolute value, right? C times xi squared is length of c squared times length of xi squared. That's the usual properties of absolute values of complex numbers. So since that c squared in length is in every term of the sum, I can factor it out. The square root of a product is the product of the square roots. When you take the square root of the square of a non-negative number, you just get it. And then you have the square root of that sum, which is just the norm of x. So that proves part A. I'll leave part B to you as an exercise. C and D are extremely important. I'm going to prove them in class, I think. But I would read the proofs before. They're not hard, but there's some ideas in them that definitely take some time to digest. And our classes are only 50 minutes long, so I'll be forced to kind of move through them quickly. Probably not as quickly as I'm talking right now, but still quickly. So one of them, the Cauchy-Schwarz inequality, I can't really say why right now, but it's very important. It gives you an upper bound on the magnitude of the inner product, two vectors. It's never more than the product of their lengths. That's what the Cauchy-Schwarz inequality says. The length of the inner product of x with y is never any more than the product of x and y's norms. The triangle inequality, I can try to draw a little picture here if I sort of visualize x as an arrow, like I'm a physicist or something like that. So there's my vector x, and then maybe here's my vector y. Yeah, x plus y by the parallelogram law. Let me try to make another copy of the vector y here and slide it up there. X plus y is the vector that emanates from their origin and terminates right there. Yeah, so that's the vector x plus y in this picture, the so-called parallelogram law. So why is this thing called the triangle inequality? Well, because it's literally saying that the length of x plus y, that is this side of that triangle, is never any more than the sum of the lengths of the other two sides. So in everyday English, this says that the length of a side of a triangle never exceeds the sum of the lengths of the other two sides, the triangle inequality. We'll prove it in class. So it has some geometric interpretation. Okay, more terminology, talking a mile a minute, but I don't want this to be long. These are terms just like from Calc 3, but these are, let's just abstract them. So if you give me an inner product space and a couple of vectors in it, I'm going to call them orthogonal if their inner product is 0. Okay, so two vectors are orthogonal if and only if their inner product is 0. A set of vectors is orthogonal if any two elements of it that are different are orthogonal. So S is orthogonal if every time you pick two vectors in S that are not the same, then their inner product is 0. I'm going to call a vector a unit vector if it has norm 1. Its length is 1, familiar terminology from calculus. A set is called orthonormal if it kind of satisfies two conditions. One, it has to be orthogonal. That's the ortho part. And second, every vector in it has to be a unit vector. That's the normal part. So an orthonormal set of vectors is a orthogonal set of unit vectors. Okay, cool. We can write down what orthonormal means in terms of the Kronecker delta function. Just if you take two vectors, xi and xj, then their inner product is, well, 0 if I is not j, that's orthogonal. Their inner product of xi with itself is the square of the norm of x, but that would be 1 if and only if the norm was 1, right? Because the square root of 1 is 1. So it's kind of a nice way of thinking about an orthonormal set. The inner product of any two vectors in it is the Kronecker delta. It's 0 or 1, depending on if the vectors are the same or not. Usual construction from calculus, if you take a non-zero vector, if you divide it by its norm, by its length, then you get a unit vector. I'll let you check that out as an exercise. Okay, the standard basis in Rn or Cn is an orthonormal set. I'll let you check out that if you take the standard inner product of any two of those basis vectors, EI and EJ, you exactly get 0 if I is not equal to j, and you get a 1 if I is equal to j. So the standard basis is an orthonormal subset, and it's a basis. A couple of more examples down here. I didn't really label these things as examples, but this set, 1, 1, and negative 1, 1 is an orthogonal set. I'll let you stop the video and check that the dot product, or the inner product, excuse me, of those two vectors is 0, standard inner product. So it's an orthogonal set, but it's not orthonormal. The length of these vectors is the square root of 2. If I take those vectors and divide them by their length, then I get unit vectors. They're still orthogonal, so that's an orthonormal set. One of the things we're going to do in section 6.2, I want to show you something called the Gram-Schmidt process that says if you take any basis for a vector space, you can always replace it with a basis in which an orthonormal basis. Orthonormal bases, our work in the near future will reveal, are particularly nice to work with. Okay, last example. I know I'm talking fast, but I want this to be short. It's kind of a hint as to how this stuff will play out in some analysis. Very interesting example, but I just want to play around with this notion of orthogonality some more. So let me let H, why is it called H? Well, maybe we'll see, but let me just call it H for a second. So it's continuous functions from the interval from 0 to 2 pi. 2 pi is not sacred here, but it's kind of a common application of it. So we'll just leave that where it's continuous. And if you're not familiar with complex valued functions, you can just sort of flow with me here that by continuous, I just mean if you change the input a little bit, you change the output a little bit. All right, so these things, you can think of a function from the interval from 0 to 2 pi into the complex plane as a path. If you like, in the complex plane, the path goes from f of 0 to f of 2 pi. And to say it's continuous just means that the path is not broken. Okay, so that's kind of what I'm thinking of. And the usual rules, sums of continuous functions are continuous. You can integrate functions that are continuous and so on. So we're going to define an inner product. I'm not going to verify it here, but an inner product on this space, the inner product of two functions is 1 over 2 pi. It's kind of a normalization factor. The integral from 0 to 2 pi of f times g bar. This is kind of like the example I mentioned earlier, but since it's complex valued, I have to put a conjugate on that g bar. Cool. Okay, now let me pick some elements of this set H. So for every integer, I'm going to define a function fn in this set H by saying fn of t is e to the I n t. Remember, by Euler's formula, e to the I times a real number is the cosine of that real number plus I times the sine of that real number. So that's an element of C, okay? It's an element of C. It's actually a point on the unit circle. So here, this Fn, if you're thinking about it as a path in C, this path lives on the unit circle. The complex length of any one of those Fn of t's is always 1. Cool. And I'm going to let S be the set of all those things. So there's infinitely many elements in my set S, one for each integer n. Notice that the complex conjugate of e to the int is e to the minus int. That follows from this formula up here. If you take the complex conjugate of e to the int, well, the complex conjugate, you make that a negative, right? I can absorb that negative into the sine function. Sine of negative x is the negative sine of x. Cosine's an even function, so you can stick the negative in there too. I know I'm talking fast, saying lots of facts here, but we can talk about them in class. But this is a fact I'm going to use below. So I'm going to verify that S is an orthonormal set. I'm going to verify that S is an orthonormal set. So what am I going to do? I'm going to take the inner product of some vectors in S. So let's suppose first that I take two different elements of S, Fn and Fm, and then M and N are not equal. Okay, well, by definition, the inner product is 1 over 2 pi times the integral of Fm times Fn bar, right? So Fn bar, I negated the exponent. And now just some exponent rules, multiply those two exponentials together. Usual calculus, antiderivative of an exponential is itself times 1 over its exponent. I'm going to evaluate that from 0 to 2 pi. Okay, so I've got my constants out front, plugging in 2 pi, plugging in 0, and e to the 0 is 1. But by Euler's formula, e to the 2 pi times an integer, e to the I times an integer times 2 pi is also equal to 1 because the cosine of an integer multiple of 2 pi is 1 and the sine of it is 0. So I end up getting that constant times 1 minus 1, I get 0. All right, so that shows that if m and n are not the same, the inner product of these things is 0. They're orthogonal. What about if n is m? Okay, well, let's just do the computation. If you take the inner product of fn with itself, then you have e to the int times e to the minus int. Well, that's e to the 0. That's just 1. 1 over 2 pi times the integral from 0 to 2 pi of dt is 1 over 2 pi times 2 pi. That's equal to 1. Right? So what have we shown? We've shown that the inner product of Fn with Fm is the Kronecker delta on Mn. It's 0 if n and m are different. It's 1 if they're the same. So that's an orthonormal set. Okay? This orthonormal set plays an extremely important role in analysis when you're thinking about functions on the circle of this basis. We'll see that working with orthonormal bases is algebraically kind of very convenient. Okay, well, that's the end of this introduction to inner product spaces. So thanks for listening.